So in your process, you are controlling the temperature of a small convection oven using our Delta V control system, because there's nothing like controlling a $10 oven with a $15,000 controller. We've been experimenting with tuning constants, and currently we have a gain of 12. Let me scroll this up. We've got a gain of 12, which is a very aggressive gain. Because this is a first order process, it's self-regulating, we'll find out later they can typically tolerate very high gain values. I want you to notice here that on the screen we're looking at the trend of the output in blue, the process variable in yellow, and the set point in white. We're very, very close to the process variable. In fact, it's hard to tell any oscillation or changes at all. But because of the very high gain we have, a gain of 12, any little bobble in the process variable gets amplified by 12, and we see those bobbles in the output. So this oscillation in the output is a magnified view of a very small oscillation in the process variable. Something I want to point out here, I said this high gain of 12 is tolerable in this process. We get very good control using that high gain. The situation would be different if this were an air valve on the output. Imagine the output were instead of driving the heating element of this, which is the electrical, let's suppose that the output were driving a pneumatic valve. What would these jagged lines do with a pneumatic valve? What would be a problem with that?
Oscillation. I mean, you're.
Why would that be a bad thing to make a valve hunt back and forth?
Well, mechanically, it's not good.
Why not?
You're putting major forces on that valve. I mean, you're going to wear it out much faster.
Right. The packing's going to wear out faster. And what about air consumption?
Oh yes, yeah.
Which costs money.
Yes.
Yeah.
That's a tangible cost over time.
Yeah.
So if we had this sort of control on a real air-actuated control valve, or even a motor-actuated control valve with mechanical wear going back and forth, that would not be acceptable. Even if the process likes it, from a maintenance standpoint, that would probably not be acceptable on the valve. Here, however, we can get away with it because why?
Slow response.
Yeah.
What's our final control element?
Heating element.
It's a heating element. We're just pulsing power to it. So who cares if our signal jumps up and down? Ooh, different pulse widths. It's not a big deal.
Don't have to grease
because,
it or anything.
Yeah, it doesn't wear in
Yeah.
the same way that a mechanical valve would.
Exactly.
So we can get away with this. However, just be aware that if this were a different story, let's say we were actuating a steam valve, air actuated or motor actuated, sending steam to a heater, this would probably not be acceptable control just for the mechanical aspect of the valve. Does that make sense?
Yeah.
So for example, on yesterday's tour, when they talked about auto-tuning, well, if you did auto-tuning in this and the auto-tuning said, well, I'd like a high gain because that process variable is coming right into set point. The auto-tuning doesn't understand, it does not know what sort of final control element you have. This may or may not be acceptable based on the type of final control element. So there's a lot more than there's a lot more to tuning than just hitting the auto-tune button. This is one example of why we need to understand the process and what's going on.